In this video, we'll be discussing interference effects that have to do with reflections that cause two different paths to which you can reach a common end. So the idea is we're going to generalize this path length difference, which I've been calling delta x. Now before we said delta x is just how much further you are from one source than the other. And the reason why is that we have assumed that the wave simply traveled from the source directly to you. In reality, though, often waves will reflect off of some surface, and so instead of directly going from the source to you, it will go to some surface, reflect off of it, and then travel to you. So what we're going to talk about is these reflection cases and how that changes some of this geometry, because this whole d sine theta part isn't necessarily going to hold together in the same way it did for this when it went straight to you, just because the two sources were at different locations. This may be a single source where it either traveled directly to you or it reflected off of something and got to you, or the might difference be which surface it reflected off of, and so on. So we're just going to talk about this in general, how it can a wave can go from two paths from and of different lengths, reach you, and therefore interfere with constructive, destructive, or partial interference. Now, the first one I'd like to talk about is something called Bragg diffraction. Note, some of these things are in the textbook and some of these not. I find a lot of these interesting. And this will be the simplest case we'll talk about. So, Bragg diffraction is talking about refraction, typically of X-rays, off of layers of crystal. The reason why it's X-rays is because we need the wavelength to be very small, because it's somewhat similar to the case before. We're going to have a maximum path length difference that's going to be related to a very small scale. In this case, the small scale is the spacing between two different layers in a crystal. So this picture right here, the black circles are atoms in a crystal, and they're going to be arranged in an even fashion. And light rays, in this case X-rays, can reflect off of these atoms. And if it reflects off of one layer versus the next layer, it'll go a slightly different distance before they reach and meet up somewhere off to the side where it's reflective off of. And you can actually figure out exactly how much farther it goes, and the answer is twice of d sine theta, where d is the distance between the two sources. It's twice because essentially d talks about how far extra it goes on one side after it reflects, and d sine theta is also how far extra has to go before it reflects, and so the total amount is 2 d sine theta. I won't work through the geometry in detail, but suffice it to say, that's just how much extra farther it goes. Note, in this case, this theta is the angle off of the surface, not off of the normal as you normally have it. So if it's a very grazing angle, then it's about the same path length difference to get to you. If it is a very steep angle, it's 90 degrees. If it comes straight down, it's 90 degrees. And therefore, it would just have to go twice this extra, the distance of the space of the atoms, as it either reflects off the top versus going all the way to the bottom, reflecting off and coming to the top. That leaves an extra amount of equal to 2d. So the n lambda part, delta x equals n lambda, that's still consistent for these cases. That's what delta x needs to be constructive or destructive, where n is going to be integers for constructive and half integers for destructive. What's going to change in each of these situations is what delta x is. So here's what delta x is for Bragg diffraction. Now you could use this, for example, to figure out how far apart atoms are spaced in a crystal. Another interesting case is with reading CDs. CDs actually work by interfering laser light off of grooves inside of them. And if you zoom in on the tracks of a CD, it'll look something like this. And what you're seeing here are little pits on a reflective surface. And this is one track here. There's another track there. There's another track there. And as this spin, there's a little laser light that will be that these tracks will move along, and you're going to have. And this, oh, by the way, this essentially acts as one long track that winds and winds and winds around the CD. So the second time it gets back to here, it's slightly offset. And what happens is that it either reflects off of the top surface, or it reflects off of the bottom, or both. So here's the cases you have. If the laser light reflects off of just the inside of the groove, so inside of here, so the entire spot is inside this hole, then on both sides, the front and the back end of the laser will reflect back at the same distance. Same thing as if it's on the top, and it will reflect back brightly. There's no basically it's all constructive interference with itself. There's no destructive interference to make this problematic. But what they do is they design it so that these grooves are about a quarter of the wavelength of light. So they choose a color of light that matches the depth of this groove by this formula. And then when it reflects off the bottom one and the top one at the same time, so that half of the spot is on the top and half of it is in the groove, the part that's on the bottom goes a little bit farther than the top that's on the part that's reflecting off the top. It specifically goes twice the depth of this groove. It goes down and then back up, which would be a half of a wavelength. And since now the bottom wave has gone half of a wavelength farther than the top, it now destructively interferes, because one half of a wavelength is a condition for destructive interference. If it reflects off both, their delta x is 0, and you get constructive interference. So what you find is a region where if the laser is running along either outside of a groove or inside of the groove, it reads that location as reading as a 1, and data on CDs is a mixture of 1s and 0s. If a patch has a boundary between a groove, being like here, then it will reflect off of both. It'll be dark, and I'll read that as a 0. So if you cut these into certain size patches, you would see something like for example, 0, 1, 0, 1, 1, 0, 0, and so on, as each segment of a certain size either had both the end of a groove, so it could reflect off of both the top and the inside, and it would read a 0, or it would be completely inside a groove, or completely on top of the surface, in which case it would read a 1. So that's how it stores the information from 0s and 1s on a CD, and same basic idea for a DVD, though the color and size of the grooves are different. So this is just a reminder. We're going to move on to something that's a little more complicated than Bragg diffraction. So just to remind ourselves what we just talked about, Bragg diffraction had a little extra distance at which it reflected. In this case, delta x was twice of d sine theta, and that if it was, you could write it as m lambda or n lambda. It doesn't really matter which letter you use. But if it was an integer number of wavelengths, it was constructive, and if it was a half integer, you would get destructive interference. Since the wavelength has to be approximately the distance d, because on the right hand side at most you can have that equal to 2d, and if you want to see bright and dark spots off at certain angles, meaning that you want to have not just the m equals 0, that central bright spot, but you also want to have bright spots off to the sides to look at for the interference, you need the left-hand side of the equation, m lambda, where m is 1 or greater, and and it has to be less than or equal to 2d. So in other words, the wavelength at the very most can be equal to twice the lattice spacing, and the size in the lattice spacing is approximately the size of an atom, and the size of an atom is approximately an angstrom, and the wavelength of a couple angstroms means, or shorter, means you have to have X-rays. That's why you use X-rays in this type of experiment. Now, the more complicated version of this is X-ray crystallography. Now, what you had from before, where you at every spot had a single atom, which then led to bright spots at certain other spots, and you get kind of more complicated patterns than I was trying to indicate because there's a lot of planes in there, is instead here you have molecules that are at every point in a lattice. And it can reflect off of different atoms in the molecule. And what you get is a lot of bright and dark spots, which they're showing you off here to the side. And from that information of where the bright and dark spots are, you can infer the size and the shape of the molecule, where the atoms are located in this molecule. So this is actually really common or sophisticated technique used to essentially image molecules. Now, again, as you can see in the picture to the left, those dots are not the shape of this molecule, and this molecule I drew is actually not the molecule that is being imaged in this case, but you can infer the shape from those dotted patterns. So the basic reason behind it is that you get constructive and destructive interference off different planes inside of these molecules. The limitation here is that in order to do X-ray crystallography, you have to have some molecule that you can make a crystal of. You can have this arrange itself in a organized repeating pattern where they're all kind of locked into common shape, which is difficult to do. But this is a very, very handy tool used by chemists and people who care about chemistry for like proteins, for example. So people who do molecular biology, to be able to understand what molecules they're actually dealing with. And from these pictures, you can infer the structure of the molecule.